Where do you clip this in?
You just kind of clip it on, and then you can like put this in your pocket. Easiest for you.
Yeah.
Can I steal it from you before you go somewhere? I'm going to swap your batteries out real quick.
Okay.
Good to go?
Awesome. Okay. Hey, everybody. I'm Stuart. We're going to be talking about binary exploitation this week. So apparently the slides are uploaded at this link, week7slides.ritsec.club. So first, a little bit about me. I'm Stuart Nevans Locke, for those of you who don't know me. I'm really into most low-level things, especially binary exploitation, but I also enjoy reversing and other such things. I'm also the leader of reverse engineering interest group. If anyone's interested in this sort of content, I totally recommend going to that to learn more of this. Then one other thing, I just really like chess. So yeah. So to start off this presentation, I just kind of want to say like what binary exploitation is, because a lot of people might have heard about it, but not really know like actually much about it. So the basic overview is that binary exploitation is pretty much just abusing some flaw in software to make it do something that it was not intended to do. So one of the recent definitions that has become really popular is looking at like software as a state machine. For those of you who know what like DFAs are, you can basically just think of software as something that has various different states, and finding like a vulnerability would be making it go to some state that the programmer did not intend. So in binary exploitation, we're pretty much just trying to take some program, some piece of software, and make it go to some state that the programmer didn't want, pretty much some state that we choose. So how do we actually find those? Typically, you want to look at things the programmer didn't think about. So for the next slide, I actually want to talk about how we would go about finding those. So to start, when like finding a vulnerability is the first thing you need to do in terms of making an exploit. First, you need your vulnerability, then you can write an exploit. And this is generally like the most time-intensive part of the binary exploitation process, because finding vulnerabilities is often really hard. So there are three main steps that I kind of break it down into. Step number one would be finding some piece of code to analyze, like some piece of code to attack. There are various like heuristics you can use to decide what piece of code to attack. I'll go a little bit more into this later, I think. But to start, some things you could do is just look for code that has like messy logic, or that has had a lot of bugs in it before, or is just like really important to the security of some software. And after you've decided on what you want to attack, you have to actually analyze what you want to attack and fully like understand it. Basically reverse engineer the piece of code you're looking at. And then finally, the third step in this would actually be like discovering your vulnerability. And there are various like known vulnerability classes. I'll go into this more later also, but just brief overview. You have some stuff like integer overflows, array out of bounds accesses, and buffer overflows, and really a ton more. But yeah. So more for step one on how we'd actually find some piece of code that we want to attack. Because if you just randomly say, oh, I want to attack this piece of code, it's really not all that likely that that's like the most efficient route to finding some vulnerability. And we don't really want to waste time. We'd ideally just find a vulnerability as quickly as possible so we can get on to exploitation, which most people think is a lot more interesting and fun. But anyways, so one of the main, I'd say most common techniques for deciding like what code you want to look at is looking to see where vulnerabilities have been found in the past. So like the CVE list is a great way of doing this. You look and say, okay, VirtualBox had some vulnerability in this function, and you go and look maybe more at that function, or look more at functions in that same file, or just functions related to the function that had a vulnerability. So basically just if some piece of code has vulnerabilities, it's probably going to have more. This is actually sometimes true because you just have one programmer who doesn't code in a very secure manner, and you can just kind of continue finding vulnerabilities in their code until eventually they're all fixed. But that's not like the only way you can decide on what to attack. Another thing you might want to do is find some like important code to security. So for example, if you take like user space in kernel space, obviously finding like a ring 0 exploit in kernel space is a lot more interesting than finding something in user space, because you'll get a lot higher privileges if you can exploit something running in the kernel rather than in user space. And another example of this is like browsers, for example. run a lot of things in sandboxes. So ideally, you'd be able to attack the parts that don't run in sandboxes. That might be harder, but it's much better like results if you can find a vulnerability in something that isn't sandboxed. And then finally, a third heuristic you can kind of use is just look for places where the logic of the programmer seems like messy or warped or whatever. Like for example, if they have a bunch of redundant checks, it's probably true that they don't really understand the code that well and are kind of just not wanting to break anything. So you might be able to kind of take advantage of that. Also, like, yeah, if there are just a ton of preconditions or no preconditions to functions, sometimes that can also be something you notice. So the next step that I mentioned before was step 2 in this finding a vulnerability process, was to actually analyze like the code. So once you've actually like said, OK, I want to attack this file or this piece of code, this folder, whatever, you actually have to do a ton of work from there, just understanding what that code is doing. Unless you happen to be an expert in that area beforehand, which is really unlikely, this is probably going to be the step that takes the most time. It just requires a lot of reverse engineering, especially if you're actually just like targeting a binary, a closed source binary. Then you have to do a ton of reverse engineering, looking at assembly and everything. That's a lot of work. So typically, it's easier to just attack open source code or just like hope your code has some open source version. Because reading C code or whatever code you want to read is just a lot easier and more fun than reading assembly. It's kind of just true. So once you kind of get some higher level understanding of the code, you want to go and figure out exactly what you control in the code. Like maybe you control some inputs to a function, and you need to figure out exactly what inputs. And you also want to figure out exactly what changes based on the inputs. Like for example, maybe if you give some various inputs, it'll actually return a value that it shouldn't or something like that. So you want to try to figure out exactly what you can control and what you can do with what you can control, looking at like side effects and such things. And one thing is a lot of people kind of overlook this step because it's definitely not glamorous. It's by far like the most boring, I'd say, part of it. But it's also incredibly important because if you don't really understand the code, it's going to be very hard to first find a vulnerability in it and second actually like, exploit that vulnerability. So finally, to the third step in this process is actually like you understand your code fully now and you want to find your vulnerability. There are two major kind of approaches to this. One is just automatic review, which is not something I'm really going to talk about a lot. That's just, there are two common ways to do this. One, you have static analysis, which is just like run some program on the code that analyzes it for you and hope it produces some interesting results. You don't actually necessarily have to have some great static analysis tool. Sometimes if you just compile software with like warnings enabled, you'll actually just find things that could turn into vulnerabilities because not everybody compiles with warnings enabled, or sometimes they just ignore the warnings. So that's actually one way you can sometimes find vulnerabilities. And then the second one is fuzzing. Again, I'm not going to really talk about this past this, but fuzzing is basically some program just tries to find bugs for you. You just tell the fuzzer, hey, attack this, and it just spams a ton of input and hopefully finds a crash. Then the other approach to actually finding vulnerabilities would be manual review. This can get you a lot like more kind of in-depth issues that are often like harder to find and wouldn't be discovered by automatic analysis. Requires a lot of time. It requires you to read a lot of code and to understand common vulnerabilities. But when you're doing this manual review, you typically want to look for common issues, which I'll talk about a little bit more. And this is also another really time-consuming step. Just finding vulnerabilities can often take forever, even after you've understood the code fully. Because also sometimes there just aren't any vulnerabilities in the code you're looking at. And there's no way to actually know if there are going to be any. So sometimes it can be really frustrating because you can just think you might be missing something when in reality you're not, and it could just be secure code. There's no way to know. So that can be annoying sometimes. So here's some like common known vulnerabilities that you should keep in mind when you're doing this sort of vulnerability discovery. So first, we often group single vulnerabilities into these things called vulnerability classes, which are basically just like groups of vulnerabilities. So for example, buffer overflows. I'm definitely going to talk more about this later. But a single buffer overflow vulnerability would be within the vulnerability class of like buffer overflows in general. And those are basically just reading too much data into something. You also have integer overflow. That's another very, very common one. And that's not a vulnerability in itself, but it is often leads to vulnerabilities. Then another one is uninitialized memory disclosure. The way I kind of describe this is just you never give some variable a value, and somehow it's used. This is often done for optimization purposes, like giving it a value. Initializing all your variables has some overhead, so sometimes programmers think, okay, whatever, I won't initialize this variable because it shouldn't be used in whatever path. But sometimes it can turn out that they're just wrong, and you're able to use some memory that hasn't actually been given a value. That's one of the more interesting ones, in my opinion, just because it's not seen a ton, but it still is out there. That's also a great one for compiler warnings, because compilers typically will warn you about this. Though people often, as I said before, just ignore compiler warnings because they don't care enough, or they don't think it can be an issue. And then the final one I'll talk about now is just printf. Many of you might or might not know this, but if you use printf incorrectly, it's actually very easy to turn into a vulnerability. If you just printf some user input, they can give these things called format specifiers. So if the user inputs, say, %i, and you do printf of whatever their string is, which in this case would be %i, what printf will actually do is it's just going to look at whatever's on the stack, and it's just going to print out whatever's on the stack as an integer. So if you just put like 500 %i's in a row, it would just dump a large portion of the stack. So there are actually some interesting ways that printf can be exploited. Like, for example, there's a %n format specifier, which seems to have been added just for the purpose of allowing these printf vulnerabilities to actually be totally exploitable. It's really strange. Yeah, it's great. It's the only format specifier that actually writes a value to memory. So yeah, for seemingly no reason, it just takes a pointer and it'll write some value to that you can control. So typically, they're actually exploitable, and these are a great way to exploit things. And not a ton of people know about it, but it can be very frustrating to exploit. I'll say that. I hate exploiting print format vulnerabilities. Very time-consuming and just annoying. Anyways, there are a ton more of these vulnerability classes. If anyone's interested, I'm happy to talk about other ones. Some things include like race conditions, use after freeze, but anyways. So now I'm actually going to talk about what I consider the interesting part, exploitation. So this is where you actually get to feel like a real hacker. So to start, let's talk about buffer overflows. I'm going to focus on stack overflows because those are a lot simpler in terms of actually exploiting than heap overflows or other overflows in general. So the root cause of buffer overflows is if you just read too much data into something that doesn't have enough storage space. So for example, if I have some array of size 50 bytes, and I store 100 bytes worth of data into that 50-byte array, that's going to cause a buffer overflow. Because what it's going to do is it's just going to save the first 50 bytes of your input into the first 50 bytes of the array, and then just save the next 50 bytes to whatever's in memory after the array. That's very, very dangerous. So there's some really famous functions for doing this, such as stir copy and gets. Gets has actually been removed in the latest C, I think, C14 it was removed in. Because if you call gets, it's basically guaranteed that you have a vulnerability in your program. That function kind of is inherently vulnerable. And it actually kind of surprises me that it took them 14 years or however long to remove it. But another one famous for this is stir copy. Stir copy copies a string to another string, but it doesn't do any bounds checking. So if you provide it a really long string to copy, it'll just keep copying past the bounds of the first string. And then there's some functions that aren't commonly known to do this, like fgets and stir ncopy and memcopy. But these all take a length parameter, like how much they should read and how much they should copy. But it's often common that you can, or not often common, but sometimes you can trick them into copying the wrong amount. For example, if the length is just some user input, like if you have a buffer of size 50 and then they say how much do you want to copy, you could just say, oh, copy 70 bytes, and it would copy 70 bytes. So those fgets, stir ncopy, and memcopy can all be vulnerable too. You don't necessarily need gets or stir copy to actually have a buffer overflow. So now to actually understand how you'd go about exploiting this, I'm going to go a little bit more in depth about how memory actually looks and how we'd actually do things, and in what we can overwrite when we write 100 bytes rather than just 50. So to start, I want to talk about stack frames. And every function in C has its own stack frame. Here's a little visualization. We have some function that has a buffer of size 16. That's 16 characters, and in most versions of C, a character is going to be exactly 1 byte. So that's going to be 16 bytes of local variables in the func thing, the func function. And then it calls the gets function, which I've already said just reads however much input you give. So that's easily going to be a buffer overflow. If you just give it 32 bytes, it's going to read 32 bytes and save that. So now to where it'll actually save those 32 bytes, if you look all the way to the right, those three things make up the stack frame. So every function has a stack frame, as I said, and each function stack frame is made up of local variables, the previous base pointer, which we won't be talking about at all. Don't worry about what that is. And then the really important thing here is the return address. Just a note, sometimes you'll have like parameters to the function in the stack frame, depending on your architecture and the number of parameters. I'm just going to ignore those to make it simpler. So in this example, we just have one local variable, buffer, which is 16 bytes. So at the bottom, you'd have 16 bytes of local variables. Then you'd have the previous base pointer, which I said we don't care about. And then you have the return address. And this is the really important part. In the case of the stack frame of func, the return address would be pointing to main. Because at the end of the func function, it would return, and it would, the assembly code has a ret instruction. And the ret instruction will just go to wherever the return address says to go. So in this case, the return address would say to go after the func call in main. So the return address would be pointing to the return 1 in code, basically. But we have this gets, so we can actually overwrite the return address to whatever we want to. So in terms of actually exploiting them, we know we can now overwrite local variables, the base pointer, which we don't care about, and the return address, which is, again, super important. So what if we actually like overwrite our return address to some function that happens to give us a shell? Like say you just had some function that's like give me a shell. If you just made the return address point to that function, it would do exactly that. You just get a shell. So it really works amazing if you just happen to have some function in your code that just gives you a shell. But obviously, most code won't just have some function that's called give me a shell and gives you a shell. So this would work great, like it would really work great if we could get around that. So 15 years ago, what people would do is they'd do this thing called shell code. They'd write their own, basically, assembly code. They'd compile it to machine code. And then they'd send their machine code. They'd overwrite in like the local variables with their machine code. And they'd say return. They'd put their return address to where their shell code lives. So they'd basically just put in some code, and then they'd return to the code they inserted. And this was called shell code. But sadly, this worked like 15 years ago, and this does not work anymore. I think this was introduced in like Windows Vista, like DEP, which I'll talk about more later. But basically, this doesn't work anymore. This is good to know about, but yeah. So just a little visualization of what we're actually able to control when you do a buffer overflow, stack buffer overflow attack. You have those same three things, the local variables, the base pointer, and the return address. And when we have this buffer overflow, we can control all of those things. So yeah. Now to talk more about the problem of like, what if we don't have some function that just does call me? And because we're in 2019, there's no shellcode possible. If we were in 2004, that would probably be doable, but sadly no. So there's this thing called ROP, which stands for Return-Oriented Programming. And basically the goal of this is to get around those protections that I talked about before that prevent you from inserting shellcode. So if you think back to our method of exporting these buffer overflows, we overwrite the local variables, we overwrite the base pointer, and we overwrite the return address. And we're overwriting exactly one stack frame. But who says we're limited to overwrite one stack frame? We can overwrite as much data as we want to. So if you think about it, we could actually just overwrite those previous stack frames too. And all those previous stack frames have return addresses that we could overwrite. So that's basically the concept behind ROP. It's a little bit more complicated in actually doing it. But the basic concept is you'd think main has a stack frame, and main stack frame is going to have local variables, base pointer, and the return address. So you just overwrite the return address in main stack frame too. So then you can return to multiple pieces in the code. And if you return to enough of these small, they're called gadgets, ROP gadgets. If you basically overwrite enough return addresses to point to each of these small ROP gadgets, you eventually have a ROP chain. And in many programs, these ROP chains can actually be totally Turing complete. They can do whatever you want them to. There are various really nice programs for finding ROP gadget, like one titled ROP gadget. And they just print out ROP gadgets that you can set your return addresses to, and they'll do various useful things. One thing to note is ROP gadgets are all often very short. Typically, they're 1 or 2 instructions long. So you might have to have a large ROP chain of 20 return addresses to do anything really important. because you can only generally execute like one or two instructions at a time for every return address you do. And generally, you're going to want to do more than just like one or two instructions in total, so you might have to have like 20 of these ROP gadgets chained together to make a fully functioning ROP chain. So that's basically the idea behind ROP. So now I'm going to talk a tiny bit about the actual mitigations and why, for example, shellcode doesn't work and what those annoying security people are doing to prevent us from actually just making this really easy. So the first mitigation, and I'd say probably the most famous, is ASLR. That stands for Address Space Layout Randomization. You sometimes will hear people call it ASLR. The basic idea is it randomizes offsets of sections in memory. So there are various sections in memory. You have like your stack, you have your heap, you're going to have the program code in there somewhere, you're going to have a bunch of libraries. And it doesn't actually like randomize where like things are relative. Like each section is a start address basically. So what ASLR does is it doesn't actually randomize where things are relative to the start address of the section. It just randomizes the start address of the section. So for example, if your stack started at address like 700, and there was something interesting in there, 16 bytes from the base of the stack, if you ran it again, the stack might start at address 900, but the interesting thing would still be 16 bytes off. So the key thing here is that offsets are all actually the same in ASLR. ASLR only applies to like sections in general. And one thing is sometimes ASLR will actually apply to like the program itself. This is, I think, different on Linux and Windows. I think it has a larger overhead to actually do on Linux. It takes like a full register. It's actually a different thing called PIE that will apply to the program on Linux, position independent execution. But basically, ASLR by itself just randomizes like the stack and heap and other sections like that. And the reason why people first thought to do this is basically you can't like return to something if you don't know where it is. So if you think back to us like overwriting the return addresses, we'd have a return address point to some useful place. But if we don't know where anything is, it's really hard to point to some useful place. And it's actually really annoying. So often exploits will require like two pieces, one to bypass ASLR and another to actually like take control of the program. Though again, this is very dependent on like how you're exploiting it. So the next mitigation is DEP. It's data execution prevention. You also often hear of it referred to like as NX, which stands for non-executable, or W XOR X, which is writable XOR executable. Basically, it's saying that you never want to have a section of memory that's both writable and executable, because you never want to be able to write something in it and then just run that immediately after. Generally, this is true for most programs. Most programs aren't doing like compilation, like just-in-time compilation, like, so they don't really care about actually writing to and executing memory. Some do, but that's pretty uncommon. Stuff like browsers do. So yeah, the idea is that it just makes it impossible to execute certain areas of memory. And this totally breaks shellcode. This was the first way to break shellcode, I think, because you can't just write some shellcode to some area and then execute it, because you'll never have an area that's both writable and executable. Though actually, yeah, as I said, that's changing a little bit with browsers, which have like just-in-time JavaScript compilation, because those need to both write code and execute it. So things are different in that area, but most things this is true. And then the final mitigation I want to talk about, and probably the simplest, is stack canaries. So stack canary, the idea behind this is you basically put some random value on the stack at the start of the function, and then you check that that value hasn't changed at the end of the function. And you put that like before the return address, basically. So if you look in this picture, this would be the same stack frame of some thing. You have the local variables, and then after the local variables, you have your stack canary. And then above the stack canary, you have the return address. So the idea is if you overwrote the local variables in stack canary and base pointer and return address, you'd have a changed stack canary. So the function wouldn't just return. It would like abort. You can't actually, with a like basic overflow, change the value of the return address without changing the value of the stack canary. Though some, especially older ones, weren't like necessarily random, and there have been various attacks on stack canaries. Now they're pretty solid and like well implemented. But if you'll notice, the last two mitigations didn't explicitly like target stack buffer overflows. They were kind of just general things that prevent you from like doing things you shouldn't be able to, basically, like run memory that shouldn't be run, and just randomizing stuff. This explicitly like targets stack overflows and totally breaks them. in most cases, I'd say stack canaries were pretty much when like stack-based buffer overflows stopped being super common and exploitable, because you really can't get around it without some other vulnerability in there. There's still sometimes you see them, especially if people just happen to compile their code without stack canaries, which shockingly happens. Like there's a very small performance overhead, but apparently some people actually care about the performance overhead. It's really completely negligible, but you know, some people just compile it without stack canaries, and then you can still do this. So that's nice. So that's everything I'm talking about for today. Does anyone have any questions? Yeah.
What resources would you recommend, like books or websites or anything, to get more information?
Books or websites. I don't necessarily have any books in mind. I know pwnable.kr was mentioned before. That's a good one. I'd say, honestly, if you're interested, I would recommend like coming to reversing. I last semester talked a lot about these in further depth. I'm probably going to do more of that this semester also. There are also some other cool websites like pwnable.tw. Also, generally, I'd recommend doing CTFs and the pwnables in those. Some of those are pretty easy. Some aren't, but those are a great learning experience. I've actually never really done any of those war games like pwnable.kr or pwnable.tw. Really, all of my experience is just from doing CTFs, and then some real world, like looking at programs and doing that. But yeah, good question. Yeah.
Just so everyone else in the room, everyone else in the room knows, what time does reversing group meet?
Good question. Yeah. Reversing group meets, I guess, Sundays 12 to 2 in Sec Lab. We're actually going to be talking about like Chrome exploitation this week. So if anybody's interested in that, definitely come. But yeah. Cool. So yeah.
Sorry for the little boinging.
I did.